Okay, you are live now.
Okay, thank you, Irai. And thank you everyone for joining today. We have one more Safari Live seminar. And today it's my pleasure to introduce Lois, who is Dr. Lois Orosa, who is a postdoc at the Safari Research Group. Lois did his PhD at the University of Santiago de Compostela in Spain. And then he was a postdoc in the University of Campinas in Brazil. He has been in research stays and internships in several companies and universities. And his current research interests are computer architecture, hardware security, reliability, memory systems, and machine learning accelerators. Thank you, everyone. Feel free to ask questions anytime. And Lois, if you're ready, please go ahead.
Thank you, Juan, for the introduction. Today I'm going to present in this paper, CODIC, a low-cost substrate for enabling custom in-DRAM functionalities and optimizations. This paper was published and presented in last year ISCA. And there is also an extended version of this paper that we have in archive. So as Juan said, feel free to interrupt me at any time. Let's go ahead. So I will start with the executive summary. So the problem we are tackling is that the timing of internal DRAM operations is fixed, which hinders the potential of DRAM for implementing new functionalities and optimizations. So our goal in this paper is to provide control over DRAM internal circuit timings to enable new functionalities and optimizations. To this end, we propose the CODIC substrate. The key idea of CODIC is to enable fine-grained control of fundamental DRAM internal circuit timings that control key basic components in the DRAM array, such as the word line, the sense amplifier, or the precharged logic. We propose and evaluate three CODIC variants, CODIC-SIG and CODIC-SIG SA, that generates signature values, and CODIC-SIG-DET that generates deterministic values. Based on our substrate, we propose three applications on the security domain that outperform the state of the art. The first application is a Codec-Based physical unclonable function. A path or physical unclonable function generates signatures unique to a device due to the unique physical variations of the device. The key idea is to use Codec-SIG to generate unique signatures that can uniquely identify a DRAM device. Our approach is 2x faster than the best state-of-the-art DRAM path. Our second application is a Codec-based call-boot attack prevention mechanism. First, in a call-boot attack, the attacker physically removes the DRAM module from the victim system and places it in a system under their control to extract secret information. Our key idea is to destroy all data at power on using Codec. Our mechanism does not incur any latency or energy at runtime. It is 2x lower latency and 1.7x lower energy than the best state-of-the-art mechanism during the DRAM power on. Our third application, this third application is not in the ISCA submission, it's in our extended version, is a Codec-based security allocation mechanism. Security allocation basically resets data in memory to 0 at the moment of the allocation, reducing the time that critical data is vulnerable to attacks. So our key idea is to use Codec to implement security allocation mechanisms with low latency, energy, and area overhead. We conclude that Codec can be used for implementing very efficient security applications, and Codec can enable new DRAM functionalities and reliability, performance, and energy optimizations. I will start with the background. DRAM is organized hierarchically. A RAM is composed of multiple DRAM chips. One DRAM chip is composed of multiple banks, and one bank is composed of multiple two-dimensional arrays of DRAM cells that are organized into rows of cells that are selected using a word line, and each cell is connected to the row buffer using the bit line. Each cell stores data in terms of charge in a capacitor, and an access transistor connects the cell to the bit line. Each bit line is connected to the sense amplifier, so it can sense and amplify the content of a cell. So the behavior of the sense amplifier and DRAM cell is orchestrated by internal DRAM signals. There are four fundamental DRAM signals that we use in this paper. The first one is the word line signal that controls the access transistor that connects the cell capacitor to the bit line. The second one is sense-P, that controls the PMOS amplifier in the sense amplifier. The third one is sense-N, that controls the NMOS amplifier in the sense amplifier. And the fourth signal is EQ, that controls the precharged unit that sets the bit line to half VDD. The DRAM memory controller can issue 4 main memory commands. The first one, of course, we have more commands, but these are the ones that are the most, let's say, common or important. The first one is activate command that activates the DRAM row containing the data. And an activate command works internally in the DRAM like following. First, the word line signal is raised to share the charge between the cell and the read line. And then the sense-N and sense-P signals are raised to sense and amplify the small charge in the cell, and as we can see in the figure. Another command is the read command that reads a column of data from the row buffer. The third is the write command that writes a column of data into the DRAM. And the fourth is the precharge command that prepares all bit lines for a subsequent activate command to a different row. And basically, precharge command just raises the EQ signal for setting the bit line to the precharge voltage level. Next,
Luis?
I will, yes.
Sorry for the interrupt. I have a question in the background, basically. So for the so we have a different signals for sensing NMOS and sensing the PMOS. So I mean there are different inputs in the DRAM module.
Oh no, these are internal signals. So you mean if that you can control the signals from the interface, from the DDR?
Yes.
No, these are the internal signals in the DRAM. So basically, the memory controller cannot control these signals. These are fixed for every activate command, and every vendor can basically tweak these signals as they like or as they find at its best. So basically, in commodity DRAM chips, we don't have any control over these signals, basically.
I see. So yeah, my issue is that so sense N is always inverse of sense P. So do we actually have different signals for them internally, or they are driving with only one source?
That's a good question. So we don't know that, right? Because we don't have the details on DRAM implementations, but that sounds like a good approach, because basically they don't need to modify these. They are always
a NOT gate.
Probably it's implement a NOT gate. Although I think that there are a slight delay between both. They can probably also insert a delay between them, but yeah.
I see.
Because we don't know the details of the implementations, but this makes sense to me. Yeah.
Yeah, thank you.
Is there any other question on the background? Okay. I will continue with the motivation and goal. So many recent works change timing between DRAM commands, but they have fixed DRAM internal circuit timings. So these signals that we talk about, right? As I just explained, the memory controller doesn't have access to these timings. They are fixed and by design. And the limitations of these fixed DRAM internal circuit timings is that they are chosen at design time and they cannot be modified. They are conservative internal circuit timings to ensure reliable operation. So they are conservative because they basically are designed for the worst case. And the memory controller does not have any knowledge or control over the internal implementations of the DRAM commands. So we as a user or the memory controller designer does not know how the DRAM manufacturer orchestrate these internal timings in the DRAM. So our work explores the potential of controlling internal DRAM circuit timings. So, and we find 3 main benefits. The first is that it enables more aggressive performance, reliability, and energy optimizations. It enables new functionalities and may open new areas of research. Our goals in this paper are two. First, enable new and enhance existing DRAM commands and optimizations by providing a low-cost substrate that enables fine-grained control over DRAM internal circuit timings. And second, design new security mechanisms that have a strong security and high performance by using the codec substrate. Yeah. Next, I will explain our codec substrate. This is an overview. So codec substrate enables greater control over DRAM internal circuit timings. It's an efficient and low-cost way to enable new functionalities and optimizations in DRAM. And codec controls the 4 key signals that we mentioned before in the background. So the word line signal that connects the DRAM cells to bit lines, the sense B and sense N signals that trigger sense amplifiers, EQ signal that triggers the logic that prepares a DRAM bank for the next access. So our codec substrate can trigger and disable internal DRAM signals in a fine-grained manner in time steps of 1 nanosecond within a time window of 25 nanoseconds. This enables a large number of possible timing combinations that allowed 304 different codec variants. And we demonstrate and evaluate 3 codec variants in this presentation. So Codec-SIG and Codec-SIG SA that generate digital signatures that depend on process variation, and Codec-DET that generates deterministic values. First, I will start explaining Codec-SIG. Codec-SIG generates digital signatures that depend on process variation, right? So the key idea is to amplify a DRAM cell that we set to the precharged voltage or half VDD. So the mechanism works as follows. In the right, we have the signals that we will see how these work. So first, the capacitor is initially set to 0 or half VDD, the value of the cell. In this example, our value is a VDD. Then we raise the word line signal. So the capacitor is connected to the bit line. And then we raise the precharge signal. So differently, for example, from activation, where we raise the word line signal and then we sense and amplify the content of the cell with the sense amplifier, we now activate the precharge logic. As a result, the final value of the cell is the precharged voltage. And in the next activate command, the sense amplifier will generate a signature value that depends on truly random process variation, because the sense amplifier will be amplified a cell that is at a half VDD level, not 1, not 0, but half VDD. Any questions about this variant? Well, this is the first variant that generates signatures in DRAM. So in the extended version of the paper, we also propose an optimization, obvious optimization, let's say. And it's based on the observation that Codec-SIG can set the voltage of the DRAM capacitor to half VDD very quickly, as we can observe in the figure of the right. So the key idea is just terminate the word line and EQ signals earlier to reduce the latency of the command without sacrificing reliability. As a result, we have the same result basically as Codec-SIG, but with lower latency. Another variant that we propose in the extended version is very similar to Codec-SIG and is called Codec-SIG SA, but basically also generates digital signatures that depends on process variation. And the key idea is sense and amplify a precharged bit line half VDD that is not connected to the DRAM cell. So, and the mechanism works like following. So we have a capacitor that is initially set to 0 or VDD. In the example is VDD, and we raise the sense N and sense P without connecting the capacitor to the bit line. Optionally, we can raise the bit line. So we grab the generated value in the cell as well. And as a result, the final value it depends on truly random process variation. So the fundamental idea is basically the same as the original Codec-SIG, that is basically amplify a voltage level that is as is at half VDD voltage to generate a random signature. And the third variant is Codec-Based. And this variant generates deterministic values. And the key idea is to activate sense N and sense B with a delay between them. The mechanism works like follow. So first, the capacitor is initially set to 0 or VDD. In the example, it's set to VDD. We raise the word line. And to generate a 0, we first raise sense N and then sense B signal sometime after sense N. And to generate a 1, this is not shown in the figure, to generate a 1, we just need to activate the signals in the inverse order. First, we need to activate sense B and then sense N. And we will generate the opposite value. We will generate a 1. As a result, Codec-Based generates 0 or 1 value deterministically. So this does not depend on the initial value of the cell, basically. How do we implement this in hardware, in DRAM? So basically, we implement a configurable delay to implement the fine-grained configurable control of the timing interval between DRAM internal circuit control signals. For example, here in the figure, we can see the circuit to generate a sense M signal. So in the top, we can see the path to generate a sense M signal for an activation command. And on the bottom, we can see that we can configure the delay of the sense M signal if we are using Codec. And we select with a max if it's a regular activate or a Codec command. The delay, we use a delay element using the 22 nanometers PTM transistor model in SPICE to simulate this and to calculate in the area overhead. And each buffer stage has a propagation delay of approximately 1 nanosecond at the output of the multiplexer. So we, in our simulations, we calculate that the total DRAM hardware overhead is about 1.1%. And regarding the changes to the DDR interface, so we need a new DRAM command to the DDR interface to leverage the codec substrate. We can integrate the new command in the standard specification without extra cost, as there is reserved space in the standard for including new commands. We also need 4 dedicated 10-bit mode registers in DRAM used to store the timings of the 4 internal timing signals that Codec can modify. And Codec uses the 16 mode register set command, or MRS, defining the DDR specification to change the contents of its mode registers. So we don't need a new command for modifying the content. Yeah. And next, I will move to the applications of our new substrate. Do you have any comments about the substrate before going into the applications?
Yeah, Lois, yes, I would like to ask you something. It's you presented several versions of Codec, but in the beginning, when you started to talk about the substrate, you mentioned that there could be up to 300 to the 4th combinations, right? Mm-hmm. So do you see any way of identifying what would be useful combinations of these signals, the signals you did already with the versions you're presenting?
So functionality-wise, I think there are not so many combinations, you know, because the most significant changes should come from changing the order of activation, right, between signals. However, Codec is not only suitable for implementing new functionalities, it could be also used for optimizations, right? You could, for example, depending on how strong is a cell or the retention time of a cell, you could keep the word line activated for some specific time, 5 nanoseconds, 6 nanoseconds, 7 nanoseconds. So here is where this fine-grained control could be useful, like for this type of optimizations where you can control the signals very precisely and to adapt, for example, for, I don't know, temperature conditions or other factors. And yeah, so depends on the application. Answering your question depends on the application.
So related to that, now that we see that there is like increasing interest on architectures or substrates that enable processing using DRAM, do you think that this fine-grained control could be useful in some way as well for these kind of computing substrates?
Yeah, I mean, they could actually. I can go to the applications and we can discuss that into the applications part, because I have a slide talking about that. Maybe I can go back to your question.
We can delay the discussion. Yeah, thank you.
Yeah, basically this is the slide. So, but yeah, basically Codec can be used in many applications, right? One is in the security domain. So these are the applications that we are evaluating in this paper. Other one is custom optimizations. I was mentioning before, maybe we can change the signals depending on the temperature or in the retention time of the cells or other variants. Also, could be useful for mitigating the process variation effects. Could be useful to improve the accuracy of the DRAM characterization. For example, an example I can think of is if you want to characterize the capacity of a cell, could be challenging, right? But maybe you could do it with Codec by, for example, reducing the time of charge sharing between the cell and the bit line. So depending how strong is the cell, you will share more or less charge, and you can detect that. So basically, you can try different charge sharing times to detect how strong is the cell, for example. In the memory controller as well, so many works try to, for example, reduce latency by reducing the timing between consecutive memory controller timing parameters, but we are violating the timing parameters specified by JDEC. And basically, when we violate these timing parameters, we don't know in which state the DRAM is when you issue the next command before you should be. So basically, having this type of control and visibility over the internal DRAM signals will at least allow you to understand in which state is your DRAM in the moment you issue a command, if the previous command didn't end yet. And the other one is related to your question, Juan, is processing in memory. This could be useful, yes, also for processing in memory, potentially. So, for example, there is one work that implements row clone. That is, row clone is an approach to copy rows in DRAM. And the original paper proposed some architectural changes in DRAM to implement this approach. And a recent paper demonstrated that they could do that by just violating some timing parameters between the activation and read and precharge to copy one row to another row. But they observe that they have many reliability issues. So they can only they cannot perform it in commodity DRAM chips reliably. Only they have some percentage of reliable operations. And this is caused in part because we don't know, and this approach that is complete DRAM is based on breaking standard timing parameters. Basically, this is not reliable because when you break these timing parameters, basically, you don't know in which state you are when you issue the next command. So basically, you don't know what is happening inside. So Codec will allow somehow having more visibility, like knowing better what is going on internally in the RAM. Does it answer your question, or do you have something else in mind, Juan?
No, I think it's fine for now. Thank you, Luis.
Yeah. So, and this work, we evaluate, propose evaluate 3 new applications in the security domain that are a codic-based physical unclonable function or path, a codic-based callboot attack prevention mechanism, and a codic-based secure deallocation mechanism. I will start with the first application, that is a physical unclonable function or path. Physical unclonable function or path generates signatures unique to a device due to the unique physical variations of the device. Paths are typically used to authenticate or identify a device. A path maps a unique input, also called challenge, to a unique output, also called response. But the limitations of the state-of-the-art paths are mainly the following. First, most of the paths, DRAM paths, have low evaluation times. Many of them require heavy filtering mechanisms to deal with inherently noisy DRAM path responses. And responses to the same challenge exhibit high variation with temperature changes, usually. And lastly, data dependency on data stored in the evaluated DRAM region. So many of them have data dependency as well. So our Codec-Based can generate signature values in DRAM that can be used as a path by amplifying a DRAM cell that we set to the precharge voltage. The characteristics of Codec-Based path are the following. Codec-Based has short evaluation latency, has repeatable path responses without relying on a filtering mechanism, is resilient to temperature changes. For example, changing the temperature that does influence much the repeatability of the path responses. And lastly, Codec-Based responses do not depend on the content of the DRAM. So if there is any questions about the first application? If not, I will go for the second application of our codec substrate, that is a prevention mechanism against callboot attacks. So a callboot attack is a physical attack on DRAM that involves hot swapping a DRAM chip and reading out the contents of the DRAM chip on another system. The attacker first disables the power and then transfers the DRAM to another system. Callboot attacks are possible because the data stored in DRAM is not immediately lost when the chip is powered off. Data in DRAM is stored in capacitors, and the data can remain in the cells long enough for it to be stolen. And this data retention effect can be even worse at low temperatures. We call our mechanism self-destruction, and it's based on the observation that it is possible to protect from callboot attacks by deleting the entire memory content during DRAM power-on. The key idea of self-destruction is to implement a low-cost in-DRAM mechanism based on codec that destroys all DRAM content during DRAM power-on. How does it work? Self-destruction is implemented completely within DRAM, so there is no intervention of the memory controller. Self-destruction can use Codec-Based, Codec-Based SA, or Codec-Deck variants to destroy data, basically because all of this data destroys the original content of the cells. Our mechanism uses a dedicated circuit within DRAM that issues codec commands back-to-back to all DRAM rows, parallelizes commands across banks, and enforces JEDEC standard timings, and destroys the entire memory content at power-on. During self-destruction, the DRAM chip does not accept any memory commands to ensure the atomicity of the process. So this happens automatically in DRAM when the DRAM is power-on, and does not introduce any performance or energy overheads at runtime, simply because this happens only at the beginning, not during runtime. Yeah. And I will wait a few seconds. If there are any questions about application 2 on callboot attacks. If not, I will continue to the third application, that is secure deallocation. Yeah. And the third application is secure deallocation. Basically, this is a third application that we propose in our extended version. So modern applications do not immediately erase data from memory when it is no longer needed. The operating system physically erases the data in a memory region when the program deallocates the memory region. Only when the physical memory is required for allocating new data. So sensitive data could remain in memory for an indefinite amount of time if we don't do it when we deallocate. So basically, secured allocation is a technique that resets data in memory to 0 at the moment of the allocation, and with the goal of reducing the time that critical data is vulnerable to attacks. Our method can use Codec-Seq, Codec-SA, or Codec-Depth variants to implement secured allocation. And Codec enables the implementation of secured allocation with very low latency, energy, and area overhead. At these approaches for implementing secured allocation are usually in software. Yeah, and next I will go to the evaluations of the 3 applications, if there is no questions. Okay, I will start with the evaluation of the codec path. So we'll evaluate the quality and performance of Codec-Seq path. We evaluate Codec-Seq path and not Codec-Seq SA because we could basically evaluate it with real DRAM chips. Codec-Seq SA couldn't be done with real chips. We only evaluate it using SPI simulations. So, and we evaluate 72 real DDR3 low power DRAM chips and 64 real DDR3 DRAM chips. We use a customized memory controller built with sovereignty. And because, so basically we cannot implement Codec-Seq in commodity DRAM chips, right? Because of the simple reason that we cannot modify the internal signals of the DRAM. This is hardwired. And for Codec-Seq, we require to change the timing of EQ and word line signals to set the cell to BDD. So what we do to evaluate Codec-Seq is to emulate Codec-Seq behavior in real DRAM chips. And this emulation consists into setting the cell to half BDD via not refreshing the DRAM rows for a long time, in our case, 48 hours. And we activate the cell to generate the signature value. And this, we observe that with this, we can emulate the functional behavior of Codec-Seq. As metrics, we use Jacquard indices to measure the similarity of 2 responses from the same memory segment or inter-Jacquard. So when you request a response from a DRAM path to the same address, let's say, you will expect to receive the same response. And this similarity is, we try to measure that with the similarity using the inter-Jacquard indices. And we also use uniqueness of 2 responses from different memory segments. So when you request 2 different paths, you expect to see very different responses, as different as possible. And this is what we call inter-Jacquard. So an ideal path should have intra-Jacquard indices close to 1. So when, as we can see in the figure, an inter-Jacquard indices close to 0, or 0 ideally. As comparison points, we use the following. First, a Codec-Seq path with no filter. This provides robust responses in most cases, in more than 99% of the cases. And with filter, that the filter basically consists into repeat the request to the path 5 times and get only the errors that repeat in all requests. So, and we observe that codec path with the filter is always robust using this methodology. Second, use the DRAM latency path that generates responses by reducing the activation latency. In our experiments, is 2.5 nanoseconds. If we don't use filter, we don't observe any robust responses, so we discarded this in our evaluation, and we use a filter of 100 path responses to compose the final response, as used in the original paper. And then we have prelat path that generates responses by reducing the pre-charge latency. In our case, we set a timing of 2.5 nanoseconds as well. So without using filter, we observe robust responses in most cases, more than 96%. But with filter, we observe that it's always robust by using 5 path responses. So we use the same filter for prelat path that for Codec-Based. Next, I will show some results about Jacquard indices. So we can see the inter-Jacquard indices in blue and inter-Jacquard indices in red. Remember that ideally inter-Jacquard should be close to 1 and inter-Jacquard should be close to 0. And we show results for the ReRAM latency path on top, prelat path on the middle, and Codec-Based path on the bottom. Yeah. And we can observe in DRAM latency path that the inter-Jacquard index is close to 1. So this is good. In prelat path and Codec-Based path, the inter-Jacquard index is 1, exactly 1, with more than 99% probability, which is very good. Regarding the inter-Jacquard indices in the DRAM latency path, they are pretty dispersed, which is not good in our experiments. In prelat path, yeah, it's also pretty far from 0, which is not good. And in our path, the inter-Jacquard indices are close to 0. We conclude that Codec-Based path is very effective at providing very similar response to the same challenge, and Codec-Based maintains uniqueness across responses to different challenges. We also evaluate the evaluation time of the paths. So we have the DRAM latency path with filter, because we didn't observe any reliable results without the filter. For prelat path, we have results with and without the filter. And for Codec-Based path, we also have results with and without a filter. We can observe that Codec-Based path with the filter is 20x faster than the DRAM latency path, and 100x faster when we don't use the filter in Codec-Based. Compared to prelat path, Codec-Based is 1.8x faster than prelat path, and also 1.8x faster than a prelat path when using the filter. So we conclude that Codec-Based path is 1.8x faster than the best state-of-the-art DRAM path. We also analyzed the robustness against temperature changes. So what we are seeing here in this figure is the intra-Jacquard index when we change the temperature. On the left, we have a temperature delta of 0, so on the default inter-Jacquard indices. Then a temperature delta of 15 degrees, so how the intra-Jacquard of the same request changes from one temperature to another temperature, but it's the same path. And the same for 25 and 55 temperature deltas. We can observe that the DRAM latency path, well, I just should explain that what we are seeing is a box and whisker plot, and the box is bounded by the first quartile, meaning that the median of the first half of the ordered set of intra-Jacquard index ranges, and is also bounded by the third quartile, so the median of the second half of the ordered set of intra-Jacquard index ranges. And the median is marked by the black line in the middle. So in the DRAM latency path, we can see that when we increase the temperature, the responses to the same path changes significantly when we increase the temperature. So we observe that DRAM latency path is not robust against temperature changes. Prelat path, however, has a very robust behavior against temperature changes. And our Codec-Based path also has a robust behavior against temperature changes. Although it's good, it's true that it's not as good, especially with 5 to 5 temperature delta variations as the prelat path. But we can conclude that Codec-Based path is very robust against temperature changes and is very close to the state of the art regarding temperature changes.
Lois?
Yes.
Any guess why Codec is doing slightly worse for 55 degrees?
Compared to prelat path?
Yes.
It's very difficult to know. It could be.
Maybe you have thought about a possible way to, figure out with other experiments. I think it looks good enough. It was just curiosity.
Yeah, I think it's good enough, especially until 25 Celsius degrees variation, right? But even after that, yeah, I think it should be good enough. But yeah, no, I don't know why really we see a slightly worse behavior as prelat path, honestly. I don't have any idea. I cannot think right now in any way to discover why, but
it might be good to, yeah, I guess there are too many variables.
Yeah, exactly. And we don't have any visibility on what is going on because these experiments we are doing them with commodity DRAMs, right? I remember these are experiments from real DRAM chips. So basically we don't have any visibility on what is going on internally in DRAM. So it's challenging to know without having a DRAM module that implements Codec in which we have more flexibility, right?
Hopefully we can have it someday. Yeah. Thank you, Lois.
Yeah, no problem. And we also evaluate the aging. So how well the path responses age. So basically we use accelerated aging techniques to artificially age our DRAM chips. We artificially age DRAM chips by operating them at very high temperatures. In our case, 125 degrees, running stress test for 8 hours. And we observed from our experiments that Codec-Based path is robust to aging. So most path responses are the same before and after aging. So most of them are basically one. So we conclude that Codec-Based path is robust also to aging. We also conduct some Nist tests. So these Nist are some standard tests for measuring the randomness of two numbers, right? So what we did here to test the randomness of path responses between different requests, different challenges, is we ran this test using different responses from different challenges. And we observed that we pass all the tests on the Nist test. So we conclude that the Codec-Based path generates high quality random signatures. If there is no questions about the evaluation of Codec-Based path, I will proceed to the evaluation of our Colwood attack prevention mechanism. Maybe there is any question on YouTube. If not, I will proceed.
No questions yet.
Okay. So for evaluating our Colwood attack mechanism, basically we evaluate the latency overheads of our mechanism that is called self-destruction at power on, implemented with Codec in our 3 variants. TCG, that stands for Trusting Computing Group. That basically what it does is issues regular write commands from the memory controller as proposed by TCG. Basically, this is a software solution to destroy data in DRAM. Lisa clone copies bulk data in DRAM from one row to another one, and row clone does the same. So we evaluate power, performance, and area overhead of Codec self-destruction compared to full main memory encryption as well. We compare to SHASHA 8 and AES 128. And for this evaluation, basically we use Ramulator, that is a DRAM simulator, and DRAM power for measuring the energy and power. These are the results. So in the y-axis, we have the time in milliseconds that takes to destroy data in the DRAM module. And in the x-axis, we have different sizes of the DRAM module. So we have from 64 megabyte DRAM module to 64 gigabyte DRAM module. And we have our 4 evaluated methods: TCG, Lisa, Rocklong, and Codic. So we observed that Codic is more than 500x faster than the software method TCG, is 2.5x faster than Lisa clone, and 2x faster than Rocklong. And this, I just want to provide some insight on why Codic is faster than Rocklong and Lisa clone, because this Rocklong and Lisa clone do this on hardware as well. They copy data inside DRAM. So this should be very fast. But the key difference between Codic and Rocklong or Lisa clone to destroy data is that Codic does not need to move data, does not need to copy data from one place to another place. So basically, it happens. The destruction happens in place. That's why the performance improvement. So, and we conclude that Codic destroys the entire content of DRAM at least 2x faster than the state of the art. So full memory, we also compare Codic with encryption, right? So full main memory encryption provides strong security guarantees at the cost of additional energy consumption and complexity. Well, yeah, I just want to remember that full main memory encryption is not always desired or not even possible because of energy restrictions or area overhead restriction, right? And our comparison points are SHA-8 and AES 128 in an Intel Atom N280. So we compare performance, power area, and processor area and DRAM area. We make 4 observations. The first one is that performance-wise, all of them has close to 0 performance overhead. So the reason why these encryption mechanisms have so low performance overhead is because they overlap the decryption with other and encryption with other functions. So in practice, is very low the overhead. However, when we talk about power, Codic self-destruction is very close to 0 because basically the destruction happens at power on. During runtime, we don't have to do anything basically. But SHA-8, the encryption mechanisms basically have between 12 and 17% power overhead, which is significant. Regarding the processor area, so Codic self-destruction does not require any or very few processor area because basically everything happens in the RAM. And SHA-8 and AES 128 has around 1% processor area overhead. Regarding DRAM area, as we mentioned before, in the hardware implementation, Codic self-destruction has 1% area overhead, while SHA-8 and AES 128 does not have DRAM overhead because they are implemented in the processor. So we conclude that Codic has no performance and power overhead at runtime, and Codic has no processor area overhead and 1.1% DRAM area overhead. Next, I will continue with evaluation of security allocation.
Lois?
Yeah.
Before you go on, can I ask you something about data destruction?
Yeah, sure.
So I'm thinking that, like, basically, if you can increase the parallelism for Codic operations, can you perform this data destruction operation much faster? So if you're
right. Yeah, we didn't optimize this process, so basically this could happen even faster. That's true. So it's not highly optimized. Basically because we don't know, we didn't want to make a lot of assumptions, right? So we make conservative assumptions about the internal architecture of DRAM. So these numbers can be valid almost for any DRAM implementation. But yeah, potentially, if you know well your internal architecture of the DRAM, you could increase the parallelism or implement, optimize this even further. Although this is also true for Lisa clone and row clone, I have to say.
Yes, but maybe they could be constrained by power more than Codic is, because they need to activate multiple rows, but Codic doesn't necessarily need to.
That's correct. That's correct. Yeah. Yeah. In that regard, when destroying data with Codic, that could be seen like energy and performance-wise is like issuing an activate command. While row clone and Lisa clone, they have more activate commands, right? So in that sense, yes, it should be more limited. Lisa clone and row clone should be more limited energy-wise. Yeah.
Okay, makes sense. Thank you.
Any other question? Okay, and last, I will show the evaluation of our secured allocation mechanism that is included in our extended version. So we evaluate latency and energy overheads of secured allocation implemented with a baseline that fills memory with 0 values using common memory write instructions, with Codic variants, with Lisa clone that copies rows in DRAM, and with row clone that also copies data in DRAM. Use the Ramulator DRAM simulator. We use a pin instrumentation tool for generating traces. We also use a box full system emulator to generate memory traces that include Linux kernel page allocations and deallocations. And we use DRAM power for retaining power and energy. So we use in the single core evaluation, we use 1 core, and in the multi-core evaluation, we use 4 cores in a typical processor configuration. Use 6 single core benchmarks, MySQL, Memcache, compiler, a Linux kernel boot up phase, some shell script, and some malloc benchmark. And we also, for the multi-core evaluation, we mix these 6 benchmarks randomly.
Lois.
Yeah.
The question about the benchmark. So do you know approximately how much of these like work in these benchmarks are memory deallocations?
So we don't have the numbers on the, but they are not much, because these are system level traces. So there are a lot going on. I mean, the most aggressive one is the malloc one, because basically it's a stress test, basically. But even though they are not, it's not 100% these operations, because you are, when you instrument the full system, you see many things that we don't identify where are they coming from, but probably operating system, memory management, basically we don't know. But yeah. I don't have a number on top of my head. We didn't measure that, but the most significant one should be the stress test on malloc operations.
Okay, yeah, but like in general, these benchmark workloads should have many memory deallocations, right?
Yeah. Some more than others. Yeah. As I said, the malloc is the most aggressive one. Actually, malloc is mainly designed for to allocate and deallocate memory. The other ones are more realistic benchmarks, like MySQL, Memcache, compilation, but the malloc test is basically a stress test.
Yeah, I see. Yeah. Thanks, Lois.
No problem. So, and these are the results of latency and energy of the single core. So the top graph is the speed up, and in the bottom we can see the energy savings. And this is for Lisa clone, Roclone, and Codic compared to a software-based approach. So we can see that Codic can improve speed up to 21% and improve energy savings up to 34%. And to show and to related to the question of how many allocations and deallocations you have in memory in this test. So basically, we didn't observe significant speed ups of Codic compared to Roclone or Lisa clone. It is still better, but it's not very significant. And this is probably caused because there are many other operations going on, not malloc and mallocs. So it's not a majority of the operations are not malloc and dialog. So the performance improvement is not so significant, although the primitive itself, Codic is like much faster than Roclone and Lisa clone. And these are the results for the 4-core evaluation. So basically saying in the top we have the speed up, and in the bottom energy savings. And we can see that with the hardware approaches with Codic, we can improve performance by 8.5% and improve energy savings by 7.5%. So we conclude that Codec-based secure allocation mechanism has high performance and energy efficient and better than the state of the art. Yeah. Any questions before I conclude? Okay, I will conclude with my executive summary. So the problem is that the timing of internal DRAM operations is fixed, which hinders the potential of DRAM for implementing new functionalities and optimizations. Our goal in this paper is to provide control over the DRAM internal circuit timings to enable new functionalities and optimizations. To this end, we propose Codec Substrate. The key idea is to enable fine-grained control of fundamental DRAM internal circuit timings that control key basic components in the DRAM array, such as the word line, the sense amplifier, or the precharge logic. We propose and evaluate 3 codec variants, Codec-SIG and Codec-SIG SA, that generate signature values, and Codec-SIG DET that generates deterministic values. Based on Codec Substrate, we propose 3 new applications in the security domain that outperform the state-of-the-art mechanisms. The first is Codec-based physical and clonable functions. A path or physical and clonable function generates signatures unique to a device due to the unique physical variations of the device. And the key idea is to use Codec-SIG to generate unique signatures that can uniquely identify a DRAM device. And it's 2x faster than the best state-of-the-art DRAM path. Second application is a Codec-based call-boot attack prevention mechanism. So in a call-boot attack, the attacker physically removes the DRAM module from the victim system and places it in a system under their control to extract secret information. And the key idea is to destroy all data at power on using Codec. And our mechanism does not include any latency or energy at runtime, and it is 2x lower latency and 1.7x lower energy than the best state-of-the-art mechanisms during DRAM power on. And the third application is a Codec-based secure deallocation mechanism. So basically, secure deallocation resets data in memory to 0 at the moment of deallocation, reducing the time that critical data is vulnerable to attacks. And the key idea is to use Codec-DET to implement secure deallocation mechanisms with low latency, energy, and area overhead. We conclude that Codec can be used for implementing very efficient security applications, and Codec can enable new DRAM functionalities and reliability, performance, and energy optimizations. So with this, I conclude my talk. I will be happy to take further questions if there is any.
Yeah, thank you very much, Lois. Very good talk. I would have a question now that you mentioned again the Codec paths. Related to them, there have been also recent works on random number generation. I think it's quite related area. So could you also generate random numbers for different applications in Codic as well? And how Codic would compare to the state of the art?
So Codic could be potentially be used for that, right? But the Codic variants that we found actually do not generate random numbers. They generate random signatures. So when you do the request to the same memory position, you will get a random number, but it will be always the same. So we didn't find any combination of commands that generate random numbers, but this does not mean that it doesn't exist, because we have many combinations of commands. That's first, but second, certainly Codic could be used to improve some of the true random number generators that already exist. For example, the ones based on violating the timing parameters. As I explained before, if we have more control of the internal timings, we could know more precisely what is going on, and we could have more control on it, and maybe select better DRAM cells that generate these random numbers. But yeah, but basically we don't know at the moment. This is
the current combinations that you have explored.
Yeah, with the exactly, but potentially yes, if you can find some source of randomness that could be exploited with Codic, sure. But basically, the random numbers we obtain now are static. Let's say they are unique to a device and unique to a memory position and random, but they are repeatable. So we couldn't find experimentally some random number generator until now. But yeah, this is possible future work.
Okay, yeah, sounds good. Are there any other questions from the audience? Mohammed, Hausong, Ataberg?
Lois?
Yeah, I have some. Oh, Hausong, please go on.
Okay, yeah, thanks. So Lois, do you have any idea that what kind of DRAM internal information that can be really good for the academics to know, so that we can develop more ideas or have a let's say have better control or increase the efficiency of existing ideas like Codic? What kind of DRAM internal information do you think will be very useful for this purpose?
I mean, for research, it will be great that we know everything, right? The architecture, how it is implemented, and everything goes on, because our life will be much easier. But I think this is not going to happen anytime soon. I think I will be more than happy if we have access to the signals that Codic wants to control. But yeah, probably it will be also useful to control some signals, not only in the DRAM array as we are proposing in Codic, but maybe in the I/O to control, I don't know, other operations like, I don't know, maybe interchanging or moving data from one bank to another bank through the global sense amplifier, for example, if you have some control over there, or maybe, I don't know, maybe even over the decoder, some more configurability on the decoder, but yeah.
Yeah, so it's basically between the let's call the DDR interface, let's say what's defined in the JEDEC standard, and the DRAM cell array that consists of cells, bitlines, word lines, and sensam. So we want to know more about what's in between these two parts, right?
Yeah, that will be great. I mean, as I said, every information that they provide, it will be great already, because really we don't know. We know some common implementations, right? What is used, but we really don't know the details. So when we are doing experiments with real DRAM chips is we have to make some assumptions, but that's it. We can assume that this manufacturer is implementing some architecture that is well known, but we really don't know. So it would be great if we can have some visibility from a research perspective, of course.
Yeah, great. Thanks.
Any other question?
Yeah, I have a question, but this is quite unrelated to Hosong's question and the discussion anyways. So the substrate you developed in Codec, can it be applied to other memory technologies as well? What will be the challenges in applying this to SRAM technology or like one of the emerging memory technologies?
So potentially, yes, right? So basically what we are proposing is some level of programmability and visibility of what is going on internally. So, or you can put it in this way, we want to have some control over the microarchitecture, and in this paper, we show the benefits of that, right? We could implement new functionalities, we could do a lot of optimizations and so on, so on. So yeah, of course, it depends on the target memory technology, but I will say that this is generally applicable to any memory technology, yes, that has some internal, signals going on, basically. So what we are advocating here is some more control over the internal behavior of the RAM, but this could be, I think, yeah, applied to any other memory technologies. Of course, the implementation details could be different, probably, but yeah, fundamentally, I think, yeah, this can be applied to any memory technology.
So I would say that enabling this ability to have these different combinations of signals can also help reveal some features, right? And some actions that you could take on any type of memory. Probably the exact thing that you can do depends on how these memory cells work.
Yeah, exactly.
So when I think of SRAM, for example, it's like in general has a much faster clock rate than DRAM devices, right? What I mean by clock rate is actually like latencies are much smaller. So maybe that could be a challenge. You would have to, I guess, have a very fine-grained control over those timings. And that means very small latencies, increments of very small latencies. So maybe rethinking codec substrate to enable the same operation without relying on that fine-grained resolution and timing control could be a challenge for SRAM devices.
Yeah, I think that makes sense. Probably also for other, non-volatile memories that are usually longer latency, it can give you even more possibilities, right? More combinations to explore.
Mm-hmm.
Yeah.
Yeah. Yeah, that's true. Yeah, I didn't think about the specific case of SRAMs, but it makes sense. I mean, yeah, that's true that the SRAMs are much faster, but the logic that you implement there is also much faster. So probably you have some flexibility there to modify some internal timings, right? But yeah, as this need to be studied in detail, as is completely implementation details. I think. Also not sure on top of my head which signals could you have in SRAM, which ones are interested to modify, or if they are, for example, for implementing new functionalities, maybe it's not so obvious as in the RAM. So basically, yeah, this needs to be studied in detail, but potentially, yes, this could be applied potentially. I mean, anyone can try to, in SPICE to implement some SRAM memory cell and see what happens when, you start to change timings over there.
Okay, yeah, makes sense.
Yeah, I think it makes sense. So how about other protection mechanisms, like related to row hammer, for example?
Your question is if we can use CODIC to protect against row hammer.
Mm-hmm.
So potentially, yes, because so if we assume that row hammer is caused mainly because of the word line activation, one way to reduce this effect of the word line activation on errors in adjacent rows could be to reduce this word line activation, right? We can do that with CODIC because we can modify the internal DRAM timings of the word line alone. So this is a potential way to mitigate a little row hammer, but we didn't study this in detail. But potentially, yes, this could be used, like in this example, for example. Yeah.
Mm-hmm.
But we didn't evaluate it because basically, yeah, we don't have the infrastructure. We don't have a DRAM module that implements CODIC. Yeah.
Mm-hmm. Yeah, I guess in simulation would also be quite challenging. But anyway, yeah, it's clear that CODIC can have a huge amount of applications, and probably it's worth to keep thinking about what else could be enabled in DRAM and in other memory technologies as well.
Yeah, exactly. CODIC could enable a lot of things potentially, but yeah, this is the three applications that we evaluate here. They are just a proof of concept, right? Mm-hmm. How three applications that work because we evaluated to have some results and we demonstrate that work, but potentially, as I said, and you also suggest, could have many other applications as well. And optimizations of latencies, energies, and so on, adapting to different behaviors, modifying the signals depending on temperature, depending on the age of the DRAM. If you can change these, if these signals are not fixed anymore, then maybe your DRAM can live much longer because you can adapt the internal DRAM timings to adapt to the degradation of the components. Maybe you can increase the charge sharing time, or there are many potential applications if you have control of these internal DRAM timings.
Mm. Yeah, I agree. Okay, yeah, thank you very much, Lois. I don't know if there are more questions from the audience. I think there is one question. Vexad is asking, are there any other signals that could be important?
So we identified these four because they are the ones related to where the data is stored in the cells, where the data is amplified in the sense amplifiers, but could be potentially others. Not sure if they will be useful. I don't know. You also need signals to control the decoders and other parts of the I/O and these things, but we didn't find them so useful. But potentially, yes. But we don't know if we could could have found these signals, we will have included them in the original paper, but we include this because we found them the most useful. But yeah, potentially, yeah. For example, the core one I/O, but yeah, not sure how you could use those signals for, or how could you improve the DRAM behavior, or if you could even implement new functionalities by controlling those signals.
Mm.
Also, it probably doesn't make sense to have a million signals controlling every signal on the DRAM. But only those that provide you more functionality, right, or more benefits. And we identify these 4 as the most useful, let's say.
Yeah, I understand and I agree, right? The 4 you detected are also those that are, let's say, more intuitive, or it's more intuitive that they are going to be useful in some way. But the good thing is that, you know, the CODIC framework also proposes a way of controlling these signals. So maybe similar approaches can also be used for different signals as well. I guess could also something else to think about in the future.
Yes, somebody found that modifying another signal that we didn't identify as useful, it can be easily incorporated to CODIC, right, to the CODIC substrate. Yeah,
makes sense. Okay, I don't see any questions in YouTube. I don't know if there are any other questions from the audience here in Zoom.
I have another one, actually.
Go ahead.
Have time for it? Okay.
I think so.
So, yeah, so CODIC has this fine-grained control over timings, right? Can this enable, or like with CODIC, can I enhance DRAM storage capabilities? Yeah, for example, can I store and read values that are neither VDD or 0 in some sort of reliable way?
So you mean like having some multi-level cell, like instead of storing 1 bit, we can store more than 1 bit in one cell?
Yeah, exactly.
Yeah, that makes sense. So you could do that with a CODIC. So basically, you in the restoration process, you could cut the restoration process in the middle. So to have 2 more levels, so have BDD, BDD 0 and 2 or 3 more levels in the middle. That will be possible for sure. You can store those intermediate values. So the problem with that approach is, okay, you can store multiple values probably with accuracy, but how do you read them? I think because you still have to rely on the sense amplifier to read those values, right? And the sense amplifier will amplify to 0 or 1. So maybe I'm missing something, but I don't see an easy way to read intermediate values between BDD and 0. But that's a good point. I mean, we can store, but we cannot read it yet unless somebody has a good idea to do it.
And I think so too, like you need probably multiple reference voltages for the sense amplifier to correctly read multi-level cells, I think.
Maybe you can, if you can modify the, the pre-charge voltage in the half VDD, if you can have multiple levels with that simple change, maybe that could be useful. I don't know. The reference level. Yeah. But not sure.
Like multi-row activation that we write partial voltage, let's call them that way, to different rows. And like in Mbit, you have some fixed reference rows with certain values of partial voltage. And then you do that multi-row activation thing, and depending on like which like reference row you're using, there might be something, I think.
Yeah, there's one solution for reading, but then, so the proposal of Ataberg, I think, was to increase the DRAM capacity, right? So if you do that, you need several rows to store, or, well, maybe not
It's
so
like
many.
Let's say 1 or 2 reference rows per subarray, but other subarray can have more capacity.
Yeah, I guess the problem would be energy-wise, I guess. It will consume some more energy because you have to activate 2 rows or 3 rows.
Yeah, and also activating those 2 rows with another arbitrary row in the subarray, it's not clear how you would do that easily, I think.
Mm-hmm. And also, it's not clear. So it's not clear how reliable is to store several levels of voltage in the cell, right? I mean, the retention time of those cells changes probably. So you don't know if you have to increase the refresh interval or reduce the refresh interval.
Also, how would the refresh even look with multi-level?
Exactly, because you have to restore to the level that was written there, right? So yeah.
Yeah. Reliability is going to be a concern. Yeah.
Yeah.
I think it's a very good discussion. For sure, it will be pretty challenging to take advantage of that. But yeah, I think the discussion was good. Thank you very much, guys. Is there anything else that you would like to discuss? If not, I guess we're almost done. Luis, anything else to add?
I don't have anything else to add. Just thank you for attending the seminar, and I hope you enjoy it.
Yeah, I think so. I think it was good and good discussion as well. It's worth to keep thinking about this direction and hopefully explore more ideas in the near future.
Yeah, I think so.
Okay, yeah, if there's no other question or comment from anyone, thank you very much, everyone, for your attention. Thank you again, Lois, for the talk. And I hope everyone has a nice evening.